Hello, welcome back. Let's talk about capacitors, a key component in electrical circuits. Capacitors store electric charge and are used in a wide range of devices, from camera flashes to defibrillators or electric vehicles. Any material that can store electric charge can be considered as a capacitor, but here I will focus on the parallel plate capacitor. We define capacitance, denoted by C, as the measure of a capacitor's ability to store charge per unit potential. Mathematically, we can express this as C is equals to Q over V, where C is the capacitance, Q is the charge stored on the capacitor, and V is the potential difference across its plates. In other words, capacitance tells us how much charge a capacitor can store for a given potential applied across its plates. Capacitance is measured in farads, although usually we need to use millifarads, nanofarads, or even picofarads. Now, let's apply this to a parallel plate capacitor, which consists of two conducting plates separated by a distance d, with area A on each plate. Our goal is to calculate the capacitance C for this specific arrangement. Because capacitance is charge over potential, basically we need to find the potential of a parallel plate configuration. When a voltage V is applied across the plates, positive charge accumulates on one plate and negative charge accumulates on the other. This creates a uniform electric field E between the plates, pointing from the positive plate to the negative plate. We already found in a previous lesson that the electric field between the plates is constant and given by E equal to sigma over epsilon naught, where sigma is the surface charge density on the plate and epsilon naught is the permittivity of vacuum. Because the plates are metallic and each plate is at a different potential, let's say 0 and V, and each plate is at a specific constant potential, each one of them, we can use the relationship between the electric field and the potential, that E is equal to minus the gradient of V. This is the derivative of V over respect to x. Because of the symmetry, this is a one-dimensional problem and I choose x to be that axis. Then so sigma d over epsilon naught. Now, from the definition of capacitance, C is equals to Q over V, and substituting V from the equation above, we get simplifying, we find C is equals to epsilon naught times area over distance. Thus, the capacitance of a parallel plate capacitor depends on the area of the plates and the distance between them, and the permittivity. Capacitors store energy due to the work done to separate the charges on the plates. The energy stored in a capacitor comes from the work required to move them against the electric field. So there's an electric field created and you move against that electric field to increase the charge. So to understand this, let's imagine gradually transferring charge dQ onto one of the plates. At any moment, the charge on the plate is Q, and the potential difference across the plates is related to the charge by V is equals to Q over C, where C is the capacitance of the capacitor again. To transfer an infinitesimal charge dQ, the small amount of work done dW is equals to V dQ, or Q over C dQ. To find the total work, and hence the energy stored in the capacitor, we need to integrate this expression as the charge builds up from 0 to Q, the final charge on the capacitor. So W is the integral from 0 to Q of Q over C dQ, and this gives which gives us U is equals to Q squared over 2C. We can also express this in terms of the potential difference V using the relationship Q is equals to CV. Thus, the energy stored in a capacitor depends on both the capacitance C and the square of the potential difference, V. This expression shows that capacitors are thus capable of storing significant energy when charged to high voltages. Similar to what we saw when we were talking about resistors, when building an electric circuit, we might need to use capacitors connected in series or in parallel. When capacitors are connected in series, the total capacitance is lower than that of any individual capacitor. This is because the charge on each capacitor is the same, but the total voltage is the sum of the individual voltages. Think about this. So the formula for capacitors in series is 1 over the total capacitance is equals to 1 over C1 plus 1 over C2 plus and so on, where C total would be the total capacitance of the set. In parallel, the total capacitance is the sum of the individual capacitance because each capacitor experiences the same potential difference and the total charge is the sum of the charges on each capacitor. There is more room for charges to pile up under this situation. The formula for capacitors in parallel then is C total is equals to C1 plus C2 plus C3 plus C4 and so on. This setup is useful when we need a large overall capacitance. Now let's talk about dielectrics, which are non-conducting materials like plastics, oil, water. These materials, when placed between the plates of a capacitor, affect the total capacitance. They increase the capacitor's capacitance by reducing the electric field inside of the capacitor. When a dielectric is inserted, the molecules align in such a way that they partially cancel the electric field from the charges on the plates. As a result, for the same charge, the potential difference V across the capacitor decreases. Since capacitance is defined as C is equals to Q over V, this means that the capacitance increases. The new capacitance with a dielectric is given by C is equals to kappa epsilon naught A over T, where kappa is the dielectric constant of the material and it reflects how well the material can reduce the electric field. For example, for air or a vacuum, K is 1, but for water it is 80. Capacitors are widely used in everyday devices. For example, in power supplies, capacitors smooth out the voltage fluctuations. In energy storage, as they store and release energy rapidly in applications like camera flashes or defibrillators. When tuning circuits, capacitors help tune radios to specific frequencies. In electric vehicles, capacitors are used to store energy that can be quickly released to power electric motors. So capacitors are devices that store energy. They behave differently in series as they behave in parallel configurations. Introducing a dielectric can increase the capacitance. Capacitors are more than just theoretical devices, they have practical applications that influence technology in many ways. See you in the next lesson, and may science be with you. Oh, wait, why did the capacitor break up with the battery? Because it found someone with more potential.